Have you ever picked something up and just wondered what it's really made of? I mean, deep down. Is it one single thing, or is it a whole jumble of different things all mixed together? Well, today, we're going to get to the bottom of it. We're breaking down the entire world of matter into two basic categories.
And we're going to start with this, a piece of granite. Yeah, I know, it's just a rock. You've probably seen it a million times. But this ordinary rock is actually the perfect place to start, because it's hiding a secret in plain sight.
So, take a good look. At a glance, it's just a rock, right? But is it truly one single uniform substance, or is there more going on here? This is the kind of question that gets to the very heart of chemistry. Are we looking at a single ingredient or a whole recipe?
And the answer is, it's a recipe. Granite isn't just one thing, it's a mixture. If you lean in close, you can see all those different specks of color. Yep, those are totally distinct minerals like quartz and feldspar and mica, all just kind of mashed together.
And this brings us to our first big idea, a heterogeneous mixture. The name sounds complicated, but it's really simple. It comes from the Greek word heteros, which just means different. And that's exactly what it is, a mix where you can literally see the different parts with your own eyes. Granite is the textbook example.
All right, that seems pretty straightforward, right? If you can see the little bits and pieces, it's heterogeneous. But what about when you can't? What about all the stuff out there that looks perfectly smooth, totally consistent, like it's made of only one thing?
Okay, so on the left, you've got our granite. No question, that's a mix. But on the right, that's just sugar dissolved in water. It looks perfectly clear. It looks completely uniform. In fact, it just looks like water. So what's the deal? Is it one thing, or is this a mixture in disguise?
And this leads us to our second big idea, a homogeneous mixture. This one comes from the Greek word homos, which means same. And that's the key. Here, the different parts are blended together so perfectly that you can't tell them apart. The sugar is still in there, the water is still in there, but they're just hanging out together. They haven't chemically changed, they're just incredibly well mixed.
And once you start looking for these, you'll see them everywhere. The air you're breathing right now, that's a homogeneous mixture of nitrogen, oxygen, and a bunch of other gases. Salt water in the ocean, same deal. Even solid things, like the steel in a skyscraper, are actually homogeneous mixtures we call alloys. They look like one pure metal, but they're not.
So this is great. We now have a way to talk about stuff that's all mixed together. But it brings up a new question, doesn't it? If mixtures are made of different things, what are those fundamental individual things actually called?
They are called pure substances. This is it. This is the other major category of all matter. A pure substance is made of only one kind of particle. Think pure gold, or pure water, or pure salt. And the most important thing is, every pure substance has its own unique, unchangeable identity.
Okay, but this is where it gets tricky. Remember that sugar water? It looks like a pure substance. So how in the world do we tell the difference? How can we be 100% sure if something is truly pure, or if it's just a really, really good mixture? Is there some kind of test we can run?
Oh yes, there is. And it's awesome. This right here is the secret identity card for every pure substance in the universe. It has a specific, unchanging, totally unique melting point and boiling point. It's like a chemical fingerprint that never, ever lies.
And just look at how incredibly specific these numbers are. At standard pressure, pure water will always boil at exactly 100 degrees Celsius. Not 99, not 101, exactly 100. And table salt, it won't even think about melting until you get it to a scorching 801 degrees. Pure titanium, you need to get over 1600 degrees. These numbers are locked in.
So here's the bottom line. A mixture, like our salt water, will boil over a range of temperatures. It gets slushy, it starts to bubble, the temperature keeps climbing. But a pure substance, it hits its boiling point and stays there until it's all turned to gas. That sharp, precise change, that is its true identity. That's how you know you're dealing with just one thing.
Okay, fine. So what? Why does any of this actually matter in the real world? Because this isn't just some abstract science concept. It is the fundamental rulebook for how we take things apart. If you want to purify something, you have to know if it's a pure substance or a mixture. Let me show you a perfect example of this in action. What we have here is a simple heterogeneous mixture. We've just got some yellow sulfur powder mixed up with some dark iron filings.
Now, the key thing to remember is that even though they're mixed, the iron is still iron and the sulfur is still sulfur. They've each kept their own unique properties.
And here's the payoff. Because iron as a pure substance has that unique property of being magnetic, we can use that property to separate our mixture. You just bring a magnet close to the test tube and voila! The magnet pulls the pure iron right out of the mix, leaving the pure sulfur behind. It's that simple. We used a unique physical property to undo the mixture.
So, let's wrap this all up. It's pretty simple when you break it down. First, everything is either a pure substance or a mixture. Second, mixtures are either heterogeneous, where you can see the parts, or homogeneous, where everything looks the same. Third, pure substances have those fixed, unique properties. That's their fingerprint. And finally, and this is the really cool part, we can use those unique properties to take mixtures apart.
So, I'll leave you with a challenge. Just look around you, wherever you are right now. Your cup of coffee, the metal in your phone, the air you're breathing. How many are pure substances, and how many are mixtures? And for those mixtures, how would you even begin to separate them? What unique properties could you exploit to pull them apart? It kind of makes you look at the world a little differently, doesn't it? Thanks for joining me.